So let's take a look at our first problem. So it says the pH of a 0.25 molar solution of benzoic acid, HC7H5O2, is measured to be 2.4. What is Ka for benzoic acid? So is our first part here. So let's go ahead and write out our formula for this first. And so benzoic acid is, we said, HC7H5O2. And so what's going to happen is that let's treat this like a Bronsted Lowry acid. So we're going to do plus water so that the benzoic acids are acid, the waters are base. And then it's going to form the conjugate base for the benzoic acid should be C7H5O2 minus, because it kept the electron from that, plus the conjugate acid for the water as the base should be hydronium, H3O plus. Okay, so we have that written out here. Now, it is the case that usually in terms of doing these, it's going to probably be a little bit simpler if we write this not in terms of the water. Instead of doing hydronium, we look at it as in terms of a hydrogen ion, basically as we would if we were doing this as if it were an Arrhenius acid. So if we did that, this basically turns into I'll go ahead and write it down here. So we have H C7H5O2 yields C7H5O2 minus plus H plus right up there. Now, this is not one of our strong acids, so that means this is going to be a weak acid, because we said if it's not one of those that we listed, it's going to be weak, so that means this is going to be at equilibrium. And now, if it's at equilibrium, then we can't assume that the 0.25 molarity of the original benzoic acid is all going to be what we end up with here. We're going to have to use some of our equilibrium stuff to this here. So its question is, what's Ka? And so, to find Ka, we're going to have to sort of set, we need to know what our concentrations are at equilibrium for each one of these things here. So to find at equilibrium, well, we're going to go up and set up our mass action expression. And so to set up the mass action expression, remember that the way we do this is we always have our start, our change, and our ending concentrations for each of these things here. So let's take a look. So what do we start with? Do we know the starting concentration of anything? Yes, because we know that it starts off at a concentration of 0.25 for the benzoic acid. So I'll say 0.25 for this. Whenever you start it off by putting in here, you don't have any of the ions. They haven't broken up yet, so we have concentrations of 0 for these two right there. Now, second thing is that do we know about what the ending concentrations of anything are? Well, it doesn't tell us, but it does tell us that the pH is 2.4. Now, the pH is going to be in terms of our hydrogen ions at equilibrium. And so that's going to tell us, if we can figure it out, basically what this equilibrium concentration is of the H+. So let's try to work that out here. So we know that pH is equal to negative log base 10 of the concentration of the H+. Bracket that off like that. The pH here is 2.4 is equal to negative log of hydrogen concentration. So that's going to be 10 to the negative 2.4. 2.4 is equal to the hydrogen concentration, hydrogen ion concentration. And so doing that, 10 to the negative 2.4 power ends up being 3.981. 3.981 times 10 to the negative third molar. So we do know the final concentration of one of these. So 3.981 times 10 to the negative third. Now that we know that the change in the hydrogen concentration started at 0, ended up 3.981 times 10 to the negative third, must be 3.981 times 10 to the negative third. All right, so now that we have that one here, we can figure out the other changes, because remember, those are in with the mole ratios. And since there is one of these and one of these and one of these, that means that this one increased by that amount, that the other of the two products is also going to increase by the same amount, 3.981 times 10 to the negative third, and to keep the mole ratio right, our reactant had to decrease by that amount, so 3.981 times 10 to the negative third. So 0 plus 3.981 times 10 to the negative third is just 3.981 times 10 to the negative third. So just our mass action expression here, then 0.25 minus that. Working that out ends up being 0.24619 right here. So we now have our three equilibrium concentrations. Now that we do that, we can set up our Ka expression. So it's going to be the two that are on the right, so the C7H5O2 minus concentration times the H plus equilibrium concentration divided by the equilibrium concentration of the original acid, which is going to be I'll just go ahead and put it in. I don't know why I'm writing out the rest of that here. So it's going to be 0.246019. I'll just draw those in because we know where they're going to go right there. So solving for Ka, when you do this here, so 3.981 times the negative third times 3.981 times the negative third divided by 0.246019 is going to end up equaling 6.4419 times 10 to the negative fifth. Nope, fifth, that's a 5. Okay, 10 to the negative fifth. Okay, now, what was our question? So what's Ka? Okay, so we have Ka. So 6.4419 times the negative fifth. I guess sig fig wise it should be 2. So 6.4 times 10 to the negative fifth would be our final value for Ka. Now the next one was what's pKa? So remember that pKa works the same way as it does for pH. It's just going to be the negative log base 10 of our Ka value, 6.4 times 10 to the negative fifth. And so when we do that, I end up getting the pKa of 4.19. So definitely a weak acid. Sort of on the stronger side as far as weak acids go, but above 2, which is roughly where your cutoff is going to be on that. And so that's how you go about using your mass action expression to be able to find out what is Ka or pKa for a particular situation. Next question, what's the concentration of hydrogen ions in a 0.11 molar solution of acetic acid? And then next question is what's the pH connected with that? So similar to what we did before, let's go ahead and write out our equation on this. I'm going to go ahead and do it in sort of the Arrhenius method, just because that's going to be a little simpler to show here. So that's going to be acetic acid. So that's hydrogen and acetate. Acetate C2H3O2. It's -1 for the valence, so it should be C2H3O2. It's not one of the 6 that we talked about that are the strong acids, and so this is going to be an equilibrium reaction. H plus ions plus our acetate ions, C2H3O2 minus, right there. All right, so with that, we want to set up as we did before. I guess I'll try to line it up with what we've got right there. So we have start, change, and end. And so I guess these just sort of go down to each spot right there. All right, so let's look at starting concentration right in here. Do we know the starting concentration of any of our substances? Well, we know right off the bat that you never add these two, so that's to be 0. Do we know the original concentration of the acetic acid? So it says in a 0.11 molar solution of acetic acid. That's how much we're putting in. So that means we're starting off with a 0.11 molar, the original concentration of the acetic acid. We're going to need to find what we end with here. So can we figure out the final concentration of anything here? Let's see, what's the concentration of hydrogen ions in a 0.11 molar solution of acetic acid? It tells us what Ka is, but it doesn't tell us like the pH, so we can't figure out what the final concentration of the hydrogen ions are, so that doesn't work. So because the fact that we don't know any of the equilibrium concentrations, we're going to have to do this in terms of variables. Look at our changes. Remember that they're all in proportion to the mole ratio, and the mole ratio here is going to be that 1 to 1 to 1 mole ratio. That makes things a little bit easier because that means that that this is going to increase by x, and this is going to increase by x, and this is going to decrease by negative x. So that means that our concentration at equilibrium of our H plus is going to be x. The concentration of our acetate ion is going to be x. 0 plus x is x. Our concentration of the acetic acid is going to be 0.11 minus x. Right there. Okay, so now that we have that, we can set up our mass action expression in terms, or set up our, our Ka equation in terms of x. So we have 1.8 times 10 to the negative fifth for Ka. It's going to equal the two concentrations that are on the product side, which are in this case going to be x and x, divided by the equilibrium concentration on the reactant side, so 0.11 minus x. All right, so two ways to go about this here. Number one, we could just go ahead, multiply all this out, solve for x. It is because the fact x times x is going to end up being x squared on top. It would turn into a quadratic equation. We'd have to use the quadratic formula. But remember that if we have very small changes, then we can do some little approximations where we can end up saying that this is approximately equal to x squared over 0.11. Because if x is small, then 0.11 minus a very small number is still very close to 0.11. We'll double check it when we get at the end. Because if we end up finding a value of x, for the most part, our rule of thumb is going to be if x is bigger than 5% of the 0.11 of the original amount, then we can't do this approximation. So if it doesn't work, we'll have to go back and use quadratic formula. But let's try this out. So 1.8 times 10 to the negative fifth equals x squared over 0.11. So we're going to go ahead and multiply both sides by 0.11, 0.11 times that. And so when doing this, we end up getting that x squared is going to be equal to, what do we get there? So 0.11 times 1.8 times, that's going to be just, actually let's go ahead and take the square root of that as well. And we end up getting, let's see, 0.001407 molar. Let me double check that. Something doesn't look right on that one. I'll assume it's right for right now. So if it's wrong, it's because I forgot to take the square root of it. If so, just take the square root of it. But I think that's what I got here. I said it written down wrong here. So once we have that, that's x, and that x is going to be basically our concentration of our hydrogen ions, because that's what we got here. It's that H plus. We're going to come down here to find that equilibrium concentration. So if we have that, if we want to find the pH is just equal to negative log of the hydrogen ion concentration, which we just found is 0.001407. So all we got to do is take negative log of that, and so doing that, I end up getting 2.85. So pH of 2.85, I guess sig fig wise, should be as 2, so I guess it would just be 2.9 for my final pH of this substance. So definitely an acid, which would make sense because we've added acetic acid into it. And so that's going to be our pH for this particular substance. Next one, nitrous acid has a pKa of 3.35 at 25 degrees Celsius. What mass of nitrous acid must be added to a liter of water to produce a solution with a pH of 4.0? So, starting off same way as we have before here. Let's write out our formula. Nitrous acid, forgot my H, HNO2. Since it's not one of our big, our strong acids, it will be in equilibrium. And so it's going to break up into our hydrogen ions plus our nitrate ions, right, like that. Because it's equilibrium, we know we're probably going to set up our mass action, so start, change, and end. Do we know any of the starting concentrations? Yes, those two right there. Do we know the original concentration of anything? We do not. And so because we don't know that, that means we're going to have to leave. Our original concentration is going to be X, right here. I guess if we have to throw other ones, we'll use y's, but we have that there. So let's see. Do we know any of the equilibrium concentrations? It does tell us that the pH ends up being 4.0. So the pH is 4.0. Then we know that 4.0 is equal to the negative log of the hydrogen ion concentration. So we can sort of, once again, move the negative over and then take that. So 10 to the negative fourth is equal to our hydrogen ion concentration just by rearranging that here. And so, okay, it's the 10 to the negative fourth. That'll work. So hydrogen ion concentration at equilibrium is 10 to the negative fourth power. So if that's true, that means the change in the hydrogen ion concentration must be 10 to the negative fourth. Because 0 plus what is 10 to the negative fourth? 10 to the negative fourth. And because of the fact that these all have a mole ratio of a 1 to 1 to 1, they're whatever one changed by, they all change by the same amount, maybe up, maybe down, but they change by the same amount. Since the reaction going to the right would have produced 10 to the negative fourth of that, it'll produce 10 to the negative fourth of this, would mean it would lose 10 to the negative fourth of this guy. So that's going to be 10 to the negative fourth power. This one is going to be x minus 10 to the negative fourth. Okay, so so once we've got that, we can go ahead and set up our Ka. So it tells us that it has, it says we have a pKa of 3.35. But to set this up, we need to find what our Ka is. And so to do that, we'll use our pKa formula. And so we know that that the pKa, which in this case is, it says 3.35, is equal to the negative log of the Ka. Okay, and so for that, same way it works. This will be 10 to the negative 3.35 power is equal to Ka. And so when we solve that for, let's see, for Ka, then ends up being, I get 4.4, so Ka is 4.4, those are both 4s, 4.46684 times 10 to the negative fourth. Okay, so I can put that in. All right, so we have 4.46866. I just messed up my little thing here. Try it again. 4.46684 times 10 to the negative fourth is equal to our two concentrations at equilibrium of our two products, 10 to the negative fourth and 10 to the negative fourth, all over x minus 10 to the negative fourth right in here. So 10 to the negative fourth times 10 to the negative fourth is just going to be 10 to the negative eighth. And so let's see here, and then we're going to multiply that x minus 10 to the negative fourth to both sides. So when we multiply it to this side, we're going to end up getting 4.46684 times 10 to the negative fourth times x minus 10 to the negative fourth here times 10 to the negative fourth here is 10 to the negative eighth. So that's going to be 4.4. Pen's getting off. Let's try it again. All right, so minus 4.46684 times 10 to the negative eighth, because we took that 10 to the negative fourth right there, and this 10 to the negative fourth, and we multiply them together, got 10 to the negative eighth. So all right, so we have that should equal 10 to the negative eighth, because that's what 10 to the negative fourth and 10 to the negative fourth times each other equals. All right, so now we just have to solve this out here. So what we'll do is we will add to both sides, plus 4.46684 times 10 to the negative eighth to both sides, plus da-da-da. We got that up right there. So that's just, this is 10 to the negative eighth, just 1 times 10 to the negative eighth. So that means just 1 times 10 to the negative eighth plus 4.46 times 10 to the negative eighth. It's going to be 5.46 times 10 to the negative eighth. So in doing this, jumping over, we end up getting 4.46684 times 10 to the negative fourth x equals 5.4 668 times 10 to the negative 8th. That's a 4 right there. Okay, so divide both sides by the 4.4668, times 10 to the negative 4th. Same thing right there. And so when I do this, I get that x is equal to 1.22 times 10 to the 4th, negative 4th. It should be molar. So that's our concentration. Now, what did it ask for? It asked for what mass of HNO3 would produce the solution with this, because this is the molar concentration of, what are we solving for? For the HNO2, right? And so that's what our X was. You can see the X is, right there. The X is right here. So we know our molar concentration of that. Now, we also know that it's in a liter of water. And so our concentration here, which is 1.22 times 10 to the negative 4th, is equal to the number of moles over 1 liter. So it's just going to be that number of moles. So I have 1.22 times 10 to the negative 4th moles of HNO2. We now need to convert to find the mass, find the grams. So 1 mole HNO2, and then how many grams of HNO2 do we have? So for this guy, let's see, should be 63.02. So 63.02 times 1.22 times 10 to the negative 4th, and so when I do that, I end up getting 0.00712 grams. Sig fig wise, looks like we should have 2 sig figs. So final answer here is going to be 0.0077 grams of HNO2. So that's going to be my final answer here. So you can see they can get a little bit complex as we get through here, but really it's just the same stuff we've done back in equilibrium, plus a little bit on what we've got here. One last one. What's the pH of a 0.45 molar solution of hydroiodic acid at 25 degrees Celsius? So hydroiodic acid, so we have HI is going to decompose, going to come apart into H plus I minus. Now let's double check, is this a strong acid? Yes, it is. Since it's a strong acid, that means we don't have to do any of our equilibrium work. We know that whatever the concentration started off as of our hydroiodic acid is going to be the same as the final concentration of the H+. So since it's a 0.45 molar solution of hydroiodic acid, that means it's also a 0.45 molar solution of H+ ions. And so if that's the case, finding the pH is relatively simple, because pH is just going to be the negative log of our concentration, 0.45 for our hydrogen ions right here. And so then it's just a matter of plugging that in right there. And so when you're doing this, I end up getting a pH of 0.34678. I guess rounded sig figs would be 52. So 0.35 is going to be the pH of our substance here. So you can sort of see, if we end up having one that's a strong acid, definitely treat it like a strong acid. It's a whole lot simpler to work out problems when they're these than when they're at equilibrium with weak acids. So yeah, in the process of doing these, check and see, is it a strong acid first? If it is, then you don't have to do near as much work, because the original concentration of the acid is the same as the final concentration of the hydrogen ions. But if it is a weak acid, then you're going to have to use your mass action expression and solve it that way.